Alright, so in the previous lectures under vectors and scalars, we have already discussed what is a vector quantity, how is it different from scalars, what are the different forms of representation of vectors, then what do we mean by parallel shifting of vector, what does it mean, right? And then components of vectors, law of projection of vectors, all these things we have already discussed in the previous lectures. In today's lecture, we are going to study different types of vectors. So under different types of vectors, we'll be studying the following types of vectors. Look here, zero vector or null vector, then parallel and anti-parallel vectors, then equal and unequal vectors, then collinear vectors, then coplanar vectors, and finally unit vector. But let me tell you one thing, in this video lecture we are not going to study in detail what is a unit vector. We'll simply try to understand what is a unit vector and how and why do we use them, right? Detailed discussion on unit vector will be in the next video lecture. So here we'll define each of these vectors and what are their significance. These things we'll try to understand in this video lecture. Alright, so the first one is zero vector or null vector. Let's try to derive the meaning from the name itself. Zero vector. Zero vector. Vector we already know. A physical quantity which has both magnitude and direction. But it's zero vector. So what can be zero in magnitude and direction? Magnitude is zero. Direction zero doesn't mean anything, right? So magnitude is zero for a vector quantity. But if magnitude is zero, how does it represent a vector quantity? How will you be able to find its direction? It's confusing, right? Let's look at a very simple example to answer all these questions and reach at the definition of zero vector, null vector. Let's take a very simple example. Suppose this is a block, right? I'm taking a very simple example. This is a block and it is applied with four forces. Simple example. Four forces from top, from bottom, from left and from right. And the block is at rest. The forces are acting but the block is at rest. Let's say from top the force is 10 Newton, from bottom 10 Newton. You are familiar with force from your previous classes, right? So here you don't have to use some very complex concepts. I'm simply using 10 Newtons, 10 Newtons. Force is represented in Newtons. This is 5 Newton, this is 5 Newton, right? This is a block. So the block is at rest. What exactly is happening? You see, four vector quantities are there acting on this block, which is a force. Here you can see these four can add up to give a value that will be force itself, a vector quantity. Means these four vector quantities will add up to give a vector quantity, not a scalar quantity. They cannot add up to give mass or length like that. They'll give force only, a vector quantity. But what they are giving here, say 10 Newton from top is being cancelled by 10 Newton from bottom. So these two will get cancelled, right? Resultant will be zero along this line. There is no force effectively. Again 5 Newton from left and 5 Newton from right. Again they'll add up and cancel each other. So resultant in this line will also be zero. So there is no net force. It is zero. But is it a scalar quantity? No, it's a vector quantity. It has both magnitude and direction because this is force, right? So here you see that these four vector quantities add up to give a vector whose magnitude is zero, right? So is it a zero vector? This is what we call zero vector. Alright, so let's look at its direction. Let's look at its direction. It's zero along this line. It's zero along this line. It's zero along this line, it's zero along this line, it's zero along this line, it's zero along this, everywhere because the resultant is zero. You can't find a net component along any of these lines, You're not going to get any value. It will be zero. So zero is along this line also, this line also, this line, whichever line you choose. Means this vector quantity doesn't have any specific direction. It is zero along this line along this line also, along this line also, along this line. It's 0 in every line. So you can't give a specific direction. We have got the definition of zero vector. A special type of vector quantity whose magnitude is 0 and doesn't have a specific direction is what we call a zero vector. And what is its significance? We generally talk about zero vector when we talk about resultant of two or more vector quantities, right? Let's write the definition. Alright, so this is the definition of zero vector. A vector quantity, a vector whose magnitude is 0 and doesn't have any specific direction. And we generally use it in connection with resultant of two or more vectors, right? Alright, so the second one, parallel and anti-parallel vectors. Again, we can understand it simply from the name itself, parallel vectors. Vectors you already know, parallel also you know. What is parallel? It's generally used in connection with lines, right? Let's try to understand from here. This is one line, right? This is another line. Are they parallel? Yes. If we extend them infinitely, wherever you want to extend them, you just go on extending. But what you are going to see, they'll never meet, they'll never intersect. So this pair of line is said to be parallel lines, right? Now simple, we have to draw vectors here. See, this is one vector. Let's say this is A vector and this is another vector. Let's say this is B vector. These two vectors are not intersecting wherever you keep them, right? Even if you shift it parallelly and place it here, it's not going to intersect. Angle between them is 0 degree, right? So these two vectors are said to be parallel vectors, right? And simply define parallel vectors as two vectors are said to be parallel if they don't intersect each other anywhere, right? What about anti-parallel vectors? Alright, so let me draw another line. Let's say this is the third line. Again, if you extend it further, it's not going to intersect. Let's assume that they are not intersecting any of these three lines, right? They're not intersecting. But now the vector is headed exactly in the opposite direction. Let's call it C vector. So this is headed in this direction, B vector is headed in this direction. They are just directed opposite to each other, exactly opposite. Angle between them is 180 degree. For example, if I shift it parallelly and place it on this line, B vector will appear something like this. This will be B vector. You can shift vectors parallelly anywhere in the space. This we have already done in the previous lectures because components are not changed. So we can do it like that. So B vector and C vector are exactly in the opposite direction, making 180 degree. So B vector and C vector or A vector and C vector are anti-parallel vectors because they are exactly in the opposite direction, right? So now we can write the definition of parallel and anti-parallel vectors. Alright, so this is the definition. Two vectors are said to be parallel if they don't intersect anywhere. That is, angle between them, angle between the two vectors is 0 degree. These two vectors are said to be parallel because they don't intersect anywhere, wherever you extend them, wherever you take them, right? And the angle between them is 0 degree. Angle between them is 0 degree. Two vectors are said to be anti-parallel if they are directed exactly opposite to each other. That is, angle between the two vectors is 180 degree. Got it? Alright, so third one, equal and unequal vectors, right? Very simple. Vectors, you know, a physical quantity having magnitude and direction. So for two vectors to be equal, both of these things, that is magnitude as well as direction, both of these two things must be same. Are you getting the point? Let me make it more clear with one example. See here, we have two vectors. One is this, another one is this. 10 units, 10 units, right? Another pair of vectors, 10 units, 5 units in the same direction. This is 10 units, this is 5 units. Another pair, this is 10 units, 10 units. So both of these vectors have same magnitude, 10 units, 10 units, same direction, right? So now let's look at each of these pairs. Here you see magnitude is same, 10 units, 10 units, but direction is different. They are not directed along the same line. So not equal vectors, unequal vectors. Here if you see magnitude is 10 units, magnitude is 5 units. Magnitude is different. One of the components, one of the things you say in magnitude and direction different, that is magnitude is different, 10 units, 5 units. Direction is same, doesn't matter, at least one thing is different, so they are not equal, unequal vectors. If you look here, magnitude is same, direction is also same. So both of these things are same for the two vectors. So these two vectors are said to be equal vectors, right? So let's write it. If A vector is equal to B vector, if A vector is equal to B vector, then magnitude of A vector, mod of A vector must be equal to magnitude of B vector. Let's write here, then if A vector is equal to B vector, then magnitude must be same, and direction. So we represent the direction like this, A cap, direction along A vector must be same as direction along B vector. So both of these conditions must be satisfied for two vectors to be called equal vectors. If they are not equal, then they are called unequal vectors. So we don't need to define unequal vectors separately. So what will be the definition? So the definition will be, for equal vectors, two or more vectors are said to be equal if all of them have the same magnitude and the same direction. Else they will be called unequal vectors. So from the definition, all these vectors are said to be equal vectors because you see all of them have the same magnitude, same arrow length and the same direction, because the angle between them is 0 degree. They are aligned along the same line. Are you getting the point? Alright, so the fourth one, collinear and non-collinear vectors. Collinear, co-worker, co-star. So co has something to do with same, like co-worker means working on the same project, working in the same company, right? Same rank, something like that. Similarly, collinear means lying along the same line, So first let's talk about two vectors to be collinear. Then they must lie along the same line, means they should be parallel. These two vectors need not have the same magnitude, but they should be along the same line, then they will be called as collinear. So whether you talk about 2 vectors, 3 vectors, 4 vectors, 5 vectors, whatever, these 3 vectors or 4 vectors or 5 vectors will be collinear if it is possible to arrange all of them in a single line, then all those vectors will be called collinear vectors, else they will be non-collinear. Let's look here. For example, this is one vector, this is another vector, this is another vector, right? Are they collinear? They are not collinear, because if you shift it parallelly, you can bring it here, that's fine. But if you bring it here by parallel shifting, I bring it here, this vector, these are not collinear because they don't lie along the same line. These two lie along the same line, but this doesn't lie along the same line, because if I extend, this is the line in which it should have been present. Then they will be called collinear, right? Let's look at this example. This is one vector, this is another vector, and this is another vector. Assume all of them are parallel. Are they collinear? Yes, they are collinear, because this can be brought here by parallel shifting. This can be brought here by parallel shifting. Let me call this vector A vector, this is B vector, this is C vector. So A vector is already here, B vector I have placed here by parallel shifting, and C vector I have placed here by parallel shifting. All these three vectors lie along the same line, so these three vectors will be called collinear, right? Now the question is it important that all these vectors should lie in the same plane, then only they will be called collinear? No, it's not important. The only condition is wherever the vectors are present, it should be possible for us to bring all those vectors by parallel shifting and arrange them in one line. If that is possible, then they are collinear. What I mean to say, look here, suppose these are two vectors present in the plane of the board and they are parallel to each other. So they can be shifted and brought in one line, so they are collinear. Let's say this is A vector and B vector. And the third vector is this one, parallel to the board but doesn't lie in the plane of the board. Let's call this vector as C vector. So are A vectors, B vectors and C vectors collinear? Yes, they are collinear, because by parallel shifting, this vector can be absorbed in the plane of the board. It is parallel to the board. Now I can shift it parallelly, bring it here. I can shift it parallelly and bring it here. Let's call this as B vector. So all these three vectors lie in the same plane. So these are collinear. So for vectors to be collinear, it is not necessary that they must lie in the same plane. The only condition is it should be possible to bring them in one line, whether by parallel shifting or simply shifting in the same plane. Getting the point? Alright. Now let's write the definition. Alright. So the definition is two or more vectors are said to be collinear. Two or more vectors. We don't define collinearity only for two vectors. Two or more vectors are said to be collinear if all of them can be arranged along one line. Irrespective of in which plane they lie, doesn't matter. They should be arranged along one line. That's it. They will be called collinear. Else they are non-collinear vectors, right? So this is an example of collinear vectors. A vector, B vector, C vector, D vector, right? Here they lie in the same plane, in the plane of the board. All of these can be shifted parallelly and arranged in one single line. So these four vectors are collinear, right? It is assumed that all these vectors are parallel. Then I am shifting it parallelly, right? Similarly, if you look here, E vector, F vector, G vector and H vector. Here E vector and G vector can be brought in one line. But what about F and H vector? No, they can't be brought in one line. So this forms non-collinear vectors, right? Some important points you must take into account. That is, first one is, for vectors to be collinear, it's not necessary that all of the vectors lie in the same plane. Like I told you, they need not lie in the same plane. It is not at all required. Only condition is it should be possible for them to get arranged in one line. That's it. And finally, collinear vectors need not have the same magnitude. Many students start asking, like for collinear vectors, is it required that they should have the same magnitude? It's not required. Only condition I have already told, along one line. Whatever be the magnitude, whatever plane they lie, doesn't matter. Got it? Coplanar vectors. Alright, so we just now studied about collinear vectors. Collinear, lying along the same line. Coplanar, lying in the same plane, right? So two or more vectors are said to be coplanar if they lie in the same plane or they can be taken in the same plane. Why they can be taken in the same plane? Because vectors can be shifted parallelly. For example, if these two vectors lie in the plane of the board and third vector is like this, parallel to the board, these three will be coplanar. The third one can be shifted parallelly and get absorbed in the plane of the board, right? So these three vectors are coplanar. So either they should lie in the same plane or they can be taken in the same plane. Then the vectors are said to be coplanar vectors. Here we'll talk about coplanar vectors under two subheadings. One is for two vectors, another is for more than two vectors, that is 3 vectors, 4 vectors, 5 vectors and so on. Okay. So first of all, I am going to talk about two vectors to be coplanar, right? Now first of all, two vectors can be either parallel, right? This is parallel. They can be either intersecting at any angle, they can be intersecting. And the third possibility is they are neither parallel nor intersecting, that is askew. This is called askew. They are not parallel, you can see. Then you'll assume if they are not parallel, they must intersect. No, this is the third possibility, that they are neither parallel nor intersecting, right? See, if you extend it further, it is in vertically upward and downward line, right? If you extend it, this is towards you and towards me. These two lines are not interfering each other at any point, so they are not going to intersect. This is called askew. These are called askew lines, right? So let's look for each of these possibilities. Vectors can be parallel, vectors can be non-parallel or simply intersecting, and the vectors can be skew, neither parallel nor intersecting. So let's look for each of them. If you talk about two vectors which are parallel, they'll always be coplanar. Very simple to visualize. If you fill the region, or the area between these two lines and you extend it further everywhere, that is the plane which will contain both of these vectors. You can see, like if I shift it parallelly, these vectors will lie in the plane of the board. So two parallel vectors will always be coplanar. What about intersecting vectors? So parallel vectors will be coplanar. What about intersecting vectors? If the two vectors are intersecting, again you can use the same concept. The region between these two vectors, this one, if you fill this area, extend it everywhere, that is the plane which will contain both of these vectors, right? You can see both of these vectors lie in the plane of the board. Both of these vectors lie in the plane of the board. Whatever be the angle, that doesn't matter. Two intersecting vectors will always be coplanar. So two intersecting vectors are always coplanar. What about askew? I mean, if one vector is like this, lying in the plane of the board, another vector is like this, another vector is like this. See here, these are not parallel, you can see, but they are not intersecting either. Getting the point? If you extend this vector, it will always be in the plane of the board, and this vector is parallel to the board, but it is not parallel to that vector, not parallel to this vector, right? So if you extend it anywhere, since this vector is parallel to the board, it's never going to intersect any point in the plane of the board. So these two will never intersect, right? So they are askew. Are they coplanar? Yes, they are coplanar. By using parallel shifting of vector. See how? If I shift it parallelly, it gets absorbed in the plane of the board, right? So now these two are coplanar vectors lying in the same plane. Getting the point? So either vector is parallel, either two vectors are parallel, or two vectors are intersecting, or two vectors are askew, doesn't matter. They all, in all the cases, the vectors will be coplanar. So we can write this statement that two vectors are always coplanar. Got it? Now let's talk about for more than two vectors, 3 vectors, 4 vectors and 5 vectors and so on, right? So I'll try to make this point clear to you by taking simple example. Let's take these two vectors, A vector, B vector and this C vector, right? These are coplanar vectors because they lie in the same plane. But there is a possibility that these 3 vectors are not coplanar. How? See, suppose this is not the C vector, or let it be C vector. Let's take another example. This is A vector, B vector and another D vector. Let's say D vector. this D vector is inclined at some angle with respect to the plane of the board. Now, can you take these three vectors in one plane? Is it possible? Never. You can take A vector and this vector, D vector, in one plane. You can take this vector and B vector in one plane. You can take A vector and D vector in one plane. You can take A vector and B vector in one plane. But you can't take all these three vectors in one plane at the same time. It's not possible. So in one case we saw A vector, B vector and C vector are coplanar. In another example we saw A vector, B vector and D vector are not coplanar. So for 3 vectors or 4 vectors or 5 vectors and so on, it is possible that vectors may be coplanar, may not be coplanar. But for 2 vectors, it is always coplanar. So finally, we can say 2 vectors are always coplanar, 3 or more vectors may or may not be coplanar. Let's write the definition. Alright, so here is the definition. 2 or more vectors are said to be coplanar if all of them lie in the same plane, or they can be taken in the same plane, as we discussed, right? Using parallel shifting of vectors. Some important points that you have to note. 2 vectors are always coplanar, irrespective of their position in the space and their orientation. Whatever be the direction in which they are headed and wherever they are present in the space, 2 vectors can always be brought in one plane. Like 2 points can always be taken on one line wherever they are present. Similarly, 2 vectors can always be taken in one plane. So they are always coplanar, right? And the second point is 3 or more vectors, that is more than 2 vectors, may or may not be coplanar, as we saw the example. So for 3 or more vectors, we need to check the coplanarity, whether they are present in the same plane or not. But for 2 vectors, we don't have to think at all. They'll always be coplanar. Got it? Alright, so the last one is unit vector. 0 vector, we have already done. A vector whose magnitude is 0 is called 0 vector. Similarly, a vector whose magnitude is unity, that is 1 unit, that is called a unit vector. Now, how do we represent a unit vector? How do we find a unit vector for a given vector? What are all mathematical operations that we can perform using a unit vector? What is its significance? All these things we'll discuss in the next video lecture. Here we are only defining the term unit vector, right? So vector whose magnitude is unity is called a unit vector. How do we represent them? What is the symbolic representation of unit vector? For example, you want to find a unit vector, or you want to represent a unit vector along the displacement of an object. So you can put a letter with cap, S cap. For example, a unit vector along the force, so F cap. A unit vector along x-axis, I cap. A unit vector along y-axis, J cap. A unit vector along z-axis, K cap, and so on. So simply you have to take a letter and put a cap on it. That is how we represent unit vector. It simply means that this is a vector whose magnitude is 1 unit. Suppose this is a vector, let's say A vector, okay, and its magnitude is 10 units. Let's say its magnitude is 10 units. I want to represent a unit vector along A vector. So I should have an arrow length which corresponds to 1 unit magnitude. So this will represent a unit vector. I can write A cap here. This will be a vector along A vector with magnitude which is equal to 1 unit, right? Okay, let's write the definition. Alright, so this is the definition. A vector whose magnitude is unity is called a unit vector. Let's take an example. Suppose a vector is given, A cap is equal to 3 by 5 I cap plus 4 by 5 J cap. This is a unit vector because if we find its magnitude, let's see, mod of A cap is equal to root of x component square, 3 by 5 square plus y component square 4 by 5 square. X component is 3 by 5, y component is 4 by 5. X component is square, y component is square, root of that will give its magnitude. This we already know from the previous lectures. So what do you get? 9 by 25 plus 16 by 25, root of this. So you get 16 plus 9, 25 by 25, root of this is equal to 1 unit. So this is an example of a unit vector. Its magnitude is unity, right? Alright, so this is all about unit vector for this lecture. In the next video lecture, we will cover this topic in complete detail. How do we find unit vector for a given vector? What all mathematical operations we can perform using unit vector? All these things we'll discuss in the next video lecture. Alright, so this is what we had to do in today's video lecture. Let's again meet in the next video lecture with full of energy. Till then, take care. Bye bye.